Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. Let's use triple integrals and cylindrical coordinates to find the volume of a cone. In this example, the cone has equation z equals the square root of x squared plus y squared in Cartesian form and is bounded by the surface where z equals 3. Let's take a look at the cone in three-dimensional form using a graphing tool. So this is the cone, and we're going to find the volume when bounded by the upper surface where z equals 3. Our first step in this process is to convert the Cartesian equation of the cone into cylindrical coordinates. So our equation in Cartesian form is z equals the square root of x squared plus y squared. So we need to go from the Cartesian system x, y and z to the cylindrical system r, theta and z. And to do this we need to substitute r cos theta for x, r sin theta for y, and z will remain the same. So if we make this substitution, we have z is equal to the square root of r squared into the bracket of cos squared theta plus sin squared theta. And using the trig substitution where cos squared theta plus sin squared theta is equal to 1, we have z is equal to the square root of r squared. And taking the positive square root gives z equal r in cylindrical coordinates. To find the volume of the cone, we need to integrate over the region E and sum infinitesimally small pieces of volume, shown here as dv. We need to unpack this and define our region using cylindrical coordinates. This will give us our limits of integration for r, theta and z, and then look at what dv equates to in this context. So let's start with the limits of integration along the z-axis. The best way to think about this is to think as though we are summing infinitesimally small pieces of volume along the z-axis between a function that defines the upper bound and one that defines the lower bound. In this case, the function at the upper bound is the surface, where z equals 3, and beneath the surface is the cone, with its apex at the origin and above the xy plane, and that's where z is equal to r. So the upper limit of integration for z is where z equals 3, and the lower limit is the equation of the cone in cylindrical coordinates, so where z is equal to r. If you remember when we looked at volumes using polar coordinates, we multiplied by a height component, which is the difference between the upper function and the lower function. Well, this is essentially the same, except that we are now using an integral to do this. Moving on to the limits of integration for r, if we look down from the z-axis, we see that a shadow in the shape of a circle centered at 0 is cast on the xy plane. The upper and lower limits of r will be along the radius of the circle, where we'll sum infinitesimally small pieces of volume. The upper bound of r is where our two surfaces, z equals 3 and z equals r, meet. If we equate the equations, we get r is equal to 3, which forms the upper limit of integration, and r begins at the origin of the circle, where r equals 0, and this forms the lower limit of integration for r. And to find the limit of integration for theta, we need to look at the coverage of r as theta rotates about the circle. As we can see, r goes full circle and therefore rotates the full 2 pi or 360 degrees. So the lower limit of theta, where theta starts, is at 0, and the upper limit of integration is where theta finishes, and in this case it's 2 pi radians. So we've defined our region using the limits of integration. Let's now unpack what we are integrating So in our case, we're integrating dV. Let's see what this translates to. So dV represents infinitesimally small pieces of volume. We're using triple integrals to sum each of these to get the total volume. Let's look at the dimensions of one of these. If we look at the green shaded region, this represents an infinitesimally small piece of volume dV. We can think of this as a tiny rectangular box where the volume is given by the height multiplied by the width multiplied by the length. So let's apply this to the green shaded region. We can see that the height is along the z-axis and it's an infinitesimally small piece of z represented by dz. The width of the box lies along the radial distance r and is an infinitesimally small piece of r represented by dr. And the length lies along the arc of the circle and is infinitesimally small. Now the arc length of a circle is given by the radius multiplied by the central angle theta. In this case, theta is infinitesimally small, represented by d theta. If we now put all these infinitesimally small dimensions together, we see that the volume dV is given by dz rdr d theta, and we sum all these pieces of volume using our triple integrals to get the total volume. So we now have our triple integral where we're integrating dz rdr d theta. So let's begin the evaluation process, beginning with the inner integral. So we're integrating from z equals r to z equals 3 dz. So using the power rule to do this, we get z, and we need to evaluate this between r and 3. And plugging in these values gives us 3 minus r. Next, let's evaluate the middle integral, where we're integrating from r equals 0 to r equals 3, 3r minus r squared dr. And using the power rule to evaluate this, we get 3r squared divided by 2 minus r cubed divided by 3. And plugging in the limits of integration, we have 27 divided by 2 minus 27 divided by 3 minus 0. And this gives us 9 divided by 2. And last but not least, let's move on to our outer integral, where we want to integrate between theta equals 0 and theta equals 2 pi of 9 over 2 d theta. Using the power rule to evaluate this, we get 9 over 2 theta. And plugging in the limits of integration, we get 9 pi minus 0. And this gives us our final solution, where the volume of the cone is equal to 9 pi.